Okay, so we actually are going to talk about the Cavendish experiment now, which is what I had to get to, but you indulged me talking about lasers first, which I don't think is fruitless. I think it's worth understanding what we're doing here and how these measurements actually work and what we're looking at. So we have a Heaney laser here. It's outputting light at 632.8 nanometers, which is that red color that you're familiar with, right? We build a lot of diode lasers that have that same color. We build them with that emission because, in part, I think because they were just meant originally for industrial applications where they would substitute for Heaney. So you have the classic red laser pointer. Seems like it's actually hard for the camera to pick that up, but I think the last time I waved it around, you could see the spot on the card. That's the same color, give or take a small error, as the 632 Heaney. All right, so we have the beam from that Heaney coming out and going into these two mirrors. And those are ubiquitous when you're working in an optics experiment. You'll almost always have two mirrors set up like that to allow you to go into the next part of your experiment. The reason is if I just had one mirror, so forget about this mirror for a second, we take it off the table, I move my laser over here. If I send my beam this way, it hits that mirror and goes into my experiment. Well, this is mounted rigidly in place, but I can use this mirror to now tip or tilt the laser beam. But that's only 1 degree of freedom, right? I want to be able to put the beam where I want it throughout the rest of the experiment. So that needs more degrees of freedom. I said one. I should have said 1 X degree of freedom and 1 Y degree of freedom. I have those 2 degrees of freedom here. 2 adjustments I can make. Degrees of freedom is our jargon as physicists. But I need an additional 2 here because then I can say, all right, well, tip the beam up a little here. So now the beam's lifted. But now tip this one down. So now the beam's flat again. It's horizontal and parallel to the table surface. But it's doing that higher. Before, if I wanted the beam to come up a little bit, I can only adjust this one mirror, tip it up. All right, now the beam's higher, but it keeps going higher, right? So having the second mirror there allows me to steer the beam where I want it. Usually the alignment into an experiment is kind of an iterative process. So I say, oh, I have 2 places where I want to see the beam downstream. I want to see it here and here. What I'll do is I'll use my first mirror to adjust the position of the beam so it's roughly where I want it at that first point. And then I'll use my second mirror to steer it to the far point. Go back to my first mirror, steer to the near point again, because it'll have moved away, right? Go back to the second mirror, go back to the far point again. So I'll have 2 alignment points. We have a little bit of a cage structure here on the table that has a couple of components in it. We can even buy little gizmos. Let me see if I'll have to go around the table. Hang on. We can buy these little gizmos with a target on them and then drop them into that cage structure. So I put that into the experiment and say, oh, get the beam centered on that crosshair. Now get it centered on that one. And that's a cute little way to do that. You don't have to use these little gizmos. You don't have to use the cage structure. You can just put a piece of paper somewhere and say, oh, here's where I want the beam to be, and keep steering back to the mark you make on a piece of paper. You could do it with a second piece of paper that you poke a hole through. That gets to be a little fussy. You can play games where you put some sort of aperture there that you can close or open or whatever. It doesn't really matter. The point is to get your beam aligned into what you want to do, you'll almost always use 2 mirrors. Okay, I've mentioned a couple times now neutral density glass. So we have some neutral density filters here that are in that beam path just to knock the power down on the laser. We measured this laser's output power, and I think it was like 2.3 milliwatts or something like that. So the lowest safety rating for lasers is a category, I think it's below 1 milliwatt if I remember correctly. So we just put some neutral density filters in there to reduce the power so that we had an eye-safe laser. And also because it made it easier to work with, because the spot would not look as blown out to us if we had this smaller amount of power that we were sending down the beam path. All right, so neutral density filters, I have described them in terms of their optical density. OD. This is a way of describing transmission stuff. We could say I transmit 10% of my power, or if you like, 0.1 of my power, or if you like, 10 to the minus 1 of my power. All right, so remember that minus 1. We could transmit 1% of the power that's incident on the glass. So 1% is 0.01, or 10 to the minus 2. Remember that minus 2. So the first filter, we would have called it an OD of 1 because it reduces the transmitted power by 10 to the minus 1. The second filter, we would call that an OD of 2 because it reduces the power by a factor of 10 to the minus 2. Or excuse me, it reduces it by a factor of 10 to the 2. It knocks it down to 10 to the minus 2 of its original power. So if I have a filter that transmits only 0.1%, so I send in a watt, I get 1 milliwatt, that would be an optical density of 3, because 10 to the minus 3 corresponds to knocking down the power that much. So we have, I don't know, a modest amount of optical density in the beam path just to make this laser easier to work with and to make us more confident that our blink reflex will keep us safe. When you shine a laser on your eye, a bunch of things can happen, and they are bad. But when you have a low power laser, and it's a continuous wave laser, so it doesn't have high peak powers instantaneously or anything like that, and it's in the visible range, you have a blink reflex that will keep you safe. That's why we're allowed to have laser pointers in regular life, right? If a laser pointer could seriously injure you, then classrooms and conference rooms would be very dangerous places because people wave those things around like they are idiots. I guess we all are. Anyway, we have our 2 mirrors here. We have a laser, 2 mirrors, and some optical density, and then we go into the experiment itself. So let's talk about that. I'm going to move the camera around, and we'll get a better look at that. Okay. So we're going in stages. The first thing we have to look at is a telescope, which we all grow up thinking means makes stuff bigger and easier to look at. And, you know, if you're a person who does imaging stuff, maybe that's how you think about a telescope. This is a Keplerian telescope. The 2 simple kinds are Galilean for Galileo Galilei and Keplerian for Johannes Kepler. We enter the first optic right here, and this optic is a focusing lens, a converging lens that causes the beam to gradually get smaller and smaller in diameter until it hits its focus, at which point it starts to diverge again. The second mirror is also a converging mirror. So if we had a point source right here, by the time it had gotten to this second telescope, excuse me, to this second lens, it would have diverged some amount. And then if we place this lens a distance away from that focus that's equal to the focal length of this lens, it will collimate the light going out. So we wanted to fiddle with the behavior of this beam a little bit. Coming out of the laser, I don't know, it looks to my eye like it's about 1 millimeter across. Coming out of here, I'd say it's a little bit bigger. Why did I do that? Well, it's because of the next part of the experiment, which has an optic in there that I wish wasn't built into the system because it makes our lives a lot harder. We're going to hit the Cavendish experiment now, and it has a concave mirror on there. If we had a flat mirror, it would not be that big of an issue. But we have a concave mirror based on some design choices that were meant to make a certain kind of detection system work back when this thing was built in 2000. We're not using the exact same detection system. We're using a more geometrical approach where we just shine a laser on this thing and look to see where it reflects to. Oof, that was a terribly constructed sentence. Look to see where it reflects that laser beam. And so we don't have the same concerns and same design principles that were at work when this thing was built. So we were going into a concave lens that would bring the beam to a focus and then let it diverge. And if we let the beam run for 5 meters or something before it hits the wall, where we're going to observe where it's moving and connect that movement of the spot back to the motion of the torsion pendulum in the Cavendish experiment, if we let that happen, the spot got blown up to be like a foot across. And it was hard to look at it and say, here's where the center of the spot is. We could have done something fussy and complicated to make that work. It would have been a huge chore. It was going to be easier if we could just manage the spot size a little bit. So we did some ray tracing and thought about this a little bit. And what we ended up doing was set up a telescope here. That's actually a little bit of a non-ideal telescope. The ideal one, this lens would be placed its focal length away from this point where the beam's at its tightest. I mean, that's going to happen by default, right? I come in here with a collimated beam, it gets focused down. And then the second lens is a distance away from that point equal to its focal length. And when I do that, a collimated beam should give me a collimated beam, but it'll be a different size. So it'll be the ratio of the two focal lengths times the original size. All right. When I do that, I'm kind of keeping my optics relatively simple. But I wanted to be able to counteract for that converging a concave mirror on the Cavendish experiment. It was going to focus the light, but then the light was going to diverge once it got past the focal point, and it was going to get to be a spot that was too big to use. So what I've done is I've made a non-ideal telescope here. And that telescope is designed such that the light coming out of this second optic is behaving as though it's diverging. And it's behaving as though it were coming from a point source, placed a distance away from that that mirror in the Cavendish experiment, such that that mirror will focus it. So if all these distances are set up just right, that mirror will send out a collimated beam of light. This is really hard to describe. I'll go draw something on a board and talk us through it, so we'll do that instead. And then we'll come back and revisit this idea.